Hello and welcome to Stories of Science. Here, we look back on humanity's long journey to understand the world. The questions, the failures, and the breakthroughs that slowly changed how we see the universe and ourselves. We tell science as stories.
The experiment that broke the universe's symmetry. Stockholm, 1957. The Nobel Prize in Physics is about to be announced. On stage stand two young theorists, Tsung-Dao Lee and Chien-Shiung Yang. Their big idea sounds almost poetic. What if the universe isn't symmetrical? Now, what does that even mean? Imagine filming a physical process, then flipping it in a mirror. For decades, physicists believed the mirrored version should behave exactly the same. This rule, called parity conservation, was treated like gravity. Rock solid. No one really questioned it. Because, well, if it ain't broke, don't fix it. Except Lee and Yang weren't buying it. In 1956, they did something that made a lot of people uncomfortable. They asked a very simple, very dangerous question. What if this symmetry just doesn't exist in weak interactions? In other words, what if the universe quietly plays favorites? Now here's the catch. A theory can be elegant, even beautiful. But nature doesn't care about elegance. It cares about evidence. And back then, there were only a handful of people who could test something this subtle, this precise. So they turned to someone who didn't take everyone believes this as an answer. Chien-Shiung Wu. At Columbia University, she was already known as one of the best in the world at studying beta decay. Her philosophy was simple: don't argue, measure. Trust, but verify, as the saying goes. When she saw the problem, she didn't spend months debating it. She got to work. The goal sounded straightforward: observe whether electrons emitted from atoms prefer a particular direction. But in practice, this was like trying to hear a whisper in the middle of a hurricane. She chose cobalt-60, a radioactive isotope perfect for probing weak interactions. Then came the real challenge. If you want to detect a directional preference, you can't have atoms spinning randomly. That would wash everything out. You need order, alignment. So how do you line up atoms? You freeze them, not put it in the fridge cold. We're talking about temperatures approaching absolute zero, where atoms barely move at all. Then you apply a strong magnetic field to force their spins into alignment, like soldiers standing at attention. Only then can you watch what the electrons actually do. If parity is conserved, the electrons should shoot out symmetrically left and right, no bias. A perfectly fair universe. But that's not what she saw. Not even close. The electrons clearly preferred one direction. This wasn't noise. This wasn't coincidence. This was statistically undeniable. And in that quiet lab, with no applause and no dramatic soundtrack, the data said something profound. The universe is not symmetrical. Decades of assumption gone. Seeing is believing. And now, everyone could see. This wasn't a minor tweak to physics. This was a rewrite of the rules. Nature, at a fundamental level, has a handedness, a preference. It doesn't stand in the middle, it leans. And then came the part that still makes people pause. In 1957, the Nobel Prize was awarded. Lee and Yang were honored for proposing the idea. But the person who proved it, who turned speculation into fact, was not included. It's a bit like someone saying, this bridge might collapse. And someone else actually stress testing it, loading it, measuring it, and proving it does collapse. But when the medals are handed out, the tester isn't on the stage. History doesn't always play fair. Wu would go on to receive many prestigious honors. But that particular prize? It was never retroactively fixed. Still, here's the deeper question. What would have happened without her? Most likely, the idea would have lingered, debated, doubted, maybe even ignored. Because science doesn't run on persuasion, it runs on proof. And she delivered exactly that. So in a way, her experiment didn't just reveal that parity is violated. It revealed something just as real, just as human. In science, truth is decided by data. But who gets remembered? That part isn't always decided by the data alone. 1912. China is in a reboot phase. The Qin dynasty is gone, but the new system hasn't fully loaded yet. Old habits still running in the background, new ideas still buffering. It's messy, unfinished, a country mid-update. And right then, in a small town in Jiangsu, a girl is born. Chien-Shiung Wu. The town, modest, easy to overlook. But her family, different story. Her father, Wu Songgaiai, was an educator. Not the quiet, go-with-the-flow kind. The kind that made neighbors pause and think, that's bold. Because he did something most people at the time wouldn't even consider. He founded a school for girls. Not because it was required. Not because it was popular. Because he believed it should exist. That distinction matters. Back then, a typical girl's life plan looked like this: housework, more housework, then marriage. Education? That was reserved for boys. But Wu Songgaiai didn't accept that. His reasoning was straightforward. If a nation wants progress, you can't leave half its people out of the upgrade. So he didn't debate. He built, opened the school, admitted girls, taught them to read, to write, to think. Today, that sounds ordinary. In the 1910s, that was like patching a system that didn't even know it had a bug. And Wu grew up inside that patched version of reality. In her world, girls studying wasn't allowed. It was normal. And that difference is everything. One is permission, the other is default setting. Even her name carries intent. Chien-Shiung. It sounds like a boy's name. That's deliberate. It signals strength. Not as encouragement, but as expectation. From the very beginning, the message was clear. You don't need to prove you belong. You just move forward. As you sow, so shall you reap. Her family planted confidence early. The household mattered. Education came first. Ideas were welcomed. Questioning mattered more than obedience. At the time, that kind of environment was rare. Zoom out, and the contrast is sharp. Many girls couldn't even read. Science? Not even part of their world. Meanwhile, she was already in structured education. Think of it like a race. Most people haven't reached the starting line. She's already a few steps ahead. And in a long race, a small lead can turn into a big gap. 1923. She's 11. She enters the Suzhou Women's Normal School. At the time, it's considered progressive. Not just teaching knowledge, but encouraging independent thinking. She spends 4 years there. Her grades are strong, but what really stands out is her mindset. She's not just solving problems, she's questioning them. A teacher explains something. She keeps going, one layer deeper. Sometimes two. Why becomes her instinct. Where there's a will, there's a way. And she keeps pushing for the why behind the what. 1927. She graduates. For a short time, she becomes a primary school teacher. Yes, she stands at the front of the classroom, but something doesn't sit right. She realizes she can teach what's already known, but she's more interested in something else. Where did this knowledge come from? Who discovered it? How did they know it was true? That question sticks. So she makes a decision. Go further. Study more. Take on something harder. Around 1930, she enrolls at National Central University. At that time, that's a top-tier path. She begins with mathematics. Makes sense. Math is the foundation of many sciences. But soon, she notices a difference. Math describes patterns. Physics explains reality. And she wants explanations. So she changes direction. From math to physics. That shift? That's a turning point. Because physics, especially experimental physics, demands two things: clear logic and practical skill. Thinking and doing. She has both. During university, she doesn't behave like a typical top student. She feels more like someone already stepping into research. She understands theory. But more importantly, she cares about how theory gets tested. Her graduation work involves Bragg's law. Sounds technical, but the idea is simple. Theory and experiment have to match. If they don't, something's wrong. And this is where one of her defining traits becomes obvious. She notices details, small ones. She watches for error. And she has a habit that's not always easy. She doesn't accept close enough. To her, close enough usually means there's a problem. In everyday life, that can feel strict. In a lab, that's precision at the highest level. After graduation, she joins a research institute. Now things change. No more textbook exercises. No more predefined answers. Now it's real questions. Unknown territory. At this point, she's no longer someone who might become a scientist. She's already doing the work. Quietly, carefully, and with a level of seriousness that sets her apart. August, 1936. She's 24. And Chien-Shiung Wu makes a decision that changes everything. She's leaving China. Not for a visit. Not for a short trip. For study. For the long game. The destination, at first, isn't Berkeley. It's the University of Michigan. She applies. Gets in. Everything looks set. And then she hears something. At the time, certain student facilities there didn't allow women to enter through the main entrance. Not a rumor. A rule. That's all it takes. She walks away. Simple logic. If you won't let me in the front door, I'm not building my future in your house. When one door closes, another opens. So she pivots. New destination. University of California, Berkeley. Fall, 1936. She arrives in California. And Berkeley, at that moment, isn't just a university. It's the center of the storm. The front line of nuclear physics. If physics had a main server, this was it. At the core of it all is Ernest Lawrence. A few years earlier, in 1931, he built the cyclotron, a machine that accelerates particles to high energies. Translation? A tool for cracking open the atom. And Berkeley is using it constantly. New particles, new data, new questions, almost every day. The atmosphere is intense. People aren't just talking about the universe. They're taking it apart, piece by piece. Wu steps into this world and matches its pace fast. She moves straight into nuclear physics experiments. And her choice is clear. Experimental physics. Not because it's easier. Because it's harder in the right way. Because it forces theory to face reality. 1937. War breaks out between China and Japan. Her original plan? Finish her studies and go home. That plan disappears. She stays. Focuses. Keeps going. Same year, she officially enters graduate study. She's surrounded by top-tier scientists, world-class labs, and pressure to match. Pressure makes diamonds. Or breaks people. She doesn't break. She starts working on beta decay. At the time, it's one of the core puzzles in nuclear physics. Unstable nuclei. Electrons flying out. Theories incomplete. Data still messy. A perfect gap to fill. And this is where her style becomes unmistakable. Data must be precise. Errors must be controlled. Results must repeat. She's not interested in results that look right. She wants results that measure right. 1938 to 1939. She publishes steadily. Not flashy, but consistent. And more importantly, she's not just following instructions. She's improving the experiments themselves. That's a different level. 1940. She earns her PhD. Still focused on beta decay. That detail matters. Because years later, this exact field will be where she reshapes physics. But right after graduation? No smooth landing. The reality of the early 1940s. Being a woman in physics was already difficult. Being Asian made it harder. Stacked odds. No shortcuts. She takes a teaching position at Smith College. Then, in 1942, she moves again to Princeton University. And here's a detail worth pausing on. She becomes the first female physics instructor in Princeton's history. Not a student, an instructor. That's not just personal progress. That's a system update. Same year, May 30, 1942. She gets married to Luke Chia-Lu Yuan. They met at Berkeley. Classic lab story. But their relationship is different from the norm at the time. This isn't one does research, the other supports. Both do research. Both think. Both argue ideas. That kind of partnership? Rare back then. Their routine is simple. Daytime, experiments. Evening, still experiments, just in conversation form. They might switch topics once in a while, but somehow, it always circles back to physics. You could call it a high-frequency intellectual loop. 1944. She joins Columbia University. And this move matters. Because now, she's no longer orbiting the center of American physics. She's inside it. December 7, 1941. The attack on Pearl Harbor. The next day, December 8, the United States declares war on Japan. And almost overnight, everything shifts. Science included. Laboratories are no longer just places to understand the world. They become places to change it. Fast. By June 1942, the U.S. Army launches a top-secret program, Manhattan Project. The objective is brutally clear. Build an atomic bomb before the war ends. No slow thinking, no academic pacing, just results. Meanwhile, Chien-Shiung Wu is teaching at Princeton University. She's just gotten married days earlier. Life is, for a moment, stable. Then history hits fast forward. Early 1943. She leaves Princeton, moves to Columbia University. This isn't just another academic stop. Columbia is one of the key research hubs feeding into the Manhattan Project. She's not stationed at Los Alamos National Laboratory, but that doesn't make her work any less important. Her role is clear. Fix experimental problems. Sounds simple. It isn't. Because at that time, nuclear physics still has gaps, especially in beta decay data, and those numbers matter a lot. If your input data is even slightly off, every calculation downstream drifts, like setting off on a journey with the wrong compass heading. You won't notice at first, but you'll end up miles off course. Her job: correct the compass, calibrate the starting point. 1944. She's working on uranium behavior in gas diffusion systems. This is part of uranium enrichment, the process that increases the proportion of fissile isotopes. No enrichment? No bomb. It's that fundamental. She also studies the distribution of electrons in nuclear fission. That connects directly to how reactions unfold. Mechanisms, energy flow, chain reactions. And here's what sets her apart: precision, repeatability, consistency. If someone runs an experiment once, she runs it 3 times. If results look close enough, she checks again and again. There's a quiet reputation building around her. She sees the errors others miss. In peacetime, that's called being meticulous. In wartime, that's called being essential. Late 1944. There's a technical issue with beta decay spectra. It's been a problem for a while, not because people ignored it, but because results kept shifting. Unstable, unreliable. She steps in, redesigns the experimental setup, tightens the conditions, runs new measurements, and this time, the data holds. Stable, consistent, usable. What does that change? Everything downstream. Theoretical models now have solid input. Calculations speed up. Decisions come faster. Would the project have continued without her? Yes. Would it have slowed down? Also yes. And in war, time isn't just money. It's outcome. Time and tide wait for no man. There's also a deeper tension here. Her work is pure physics. Measurement, verification, accuracy. But the end goal? A weapon. She's not in the room where decisions are made, but her data feeds into those decisions. That's a reality many scientists faced at the time. Do the work? Or step away? She chooses to do it. Not out of abstraction, but because the world is already in motion. July 16, 1945. The first atomic bomb is tested in New Mexico. Trinity nuclear test. It works. August 6, 1945. Hiroshima. August 9, 1945. Nagasaki. By August 15, the war is effectively over. For the first time in history, science has altered the course of war at this scale. Wu isn't involved in deployment. She's not part of the decision chain. But her Her measurements are part of the system that made it possible. After the war, people start asking hard questions. Should scientists be responsible for how their work is used? There's no single answer. There never has been. She doesn't publish long reflections about it. She does what she has always done: experiment, measure, verify. But one thing is clear: between 1943 and 1945, she undergoes a shift from academic researcher to a key contributor inside a national mission. Not the most visible role, but a critical one. She didn't design the bomb. She made sure the details worked. And at that level of engineering, details aren't small things. They are everything. September 1945. The war is over. The noise fades. And the lights come back on in the labs. For Chien-Shiung Wu, that means one thing: back to work. Not easy work. The hard kind. The kind where results don't come quickly, and mistakes don't forgive you. 1946. She officially takes a research position at Columbia University. Top-tier environment. Top-tier competition. No shortcuts. And she makes a choice. She doesn't pivot to something fashionable. She doubles down on beta decay. At the time, this is one of the messiest problems in nuclear physics. Not because there's no theory. There is. But the data, not clean enough. Too many results floating in that uncomfortable zone. Probably right. Close enough. That's not her standard. Not even close. Close only counts in horseshoes and hand grenades. Not in precision physics. From 1947 to 1950, she publishes paper after paper. Different setups. Same mission. Make beta decay measurable. Clearly. Reliably. She refines detectors, reworks experimental designs, cuts down systematic error, tightens everything, and her results have a signature. Other scientists can reproduce them and get the same answer. That's gold in physics, because if it can't be repeated, it can't be trusted. 1952. She's promoted to associate professor. That's more than a title. It's a signal. She's no longer just doing strong work. She's becoming an authority. By the early 1950s, she has a quiet reputation. If you have a beta decay problem, you go to her. Like calling the best engineer when your system crashes. Not because she's the loudest, because she's the most reliable. Later, she gathers years of this work into a book. Not a popular science read. A serious reference. Published in 1965. Title: Beta Decay. Straightforward. No decoration. And it quickly becomes a standard. Physicists use it not because it's easy to read, but because it's accurate. Her teaching style? Same energy. Strict. Direct. Students submit reports. If the data isn't solid, she doesn't soften it. She points it out. Clearly. No maybe. No almost. She's not grading effort. She's judging whether it's publishable. 1958. She becomes a full professor and is elected to the National Academy of Sciences. At the time, that's one of the highest recognitions a scientist can receive. By now, she's not rising talent. She's already at the top of experimental physics. Active, respected, trusted, and right at that moment, a question appears. Spring 1956. Two theorists start re-examining old assumptions. Tsundao Li and Chen-Ning Yang. They focus on something that everyone thinks is untouchable: parity conservation. The idea is simple. Nature should behave the same in a mirror. Flip a physical process left to right. Nothing changes. For decades, this has been treated as obvious. Too obvious to even test. But they look closer. June 1956. They review existing experimental data, and they notice something uncomfortable. In weak interactions, there's no direct proof that parity is conserved. Think about that. Everyone assumes it's true, but no one has actually measured it. It's like a default setting nobody ever checked. And now the question is on the table. Does parity really hold in weak interactions? The reaction across physics? Split. Some say, worth investigating. Others say, why bother? Because if it turns out to be wrong, it's not a small fix, it's a rewrite. They don't stop at theory. They know this can't be settled by argument. It needs an experiment. A precise one. Not close enough. Not probably. Something definitive. So they start looking for the right person. Not just any experimentalist. Someone who can push error margins down. Someone who won't let expectations bias the result. Someone who trusts data more than theory. One name comes up, again and again. Wu. Summer, 1956. They reach out to her. No hype. No dramatic pitch. Just a question. Can you test this? She doesn't answer immediately. She studies the problem. Looks at existing data. Thinks it through. And she realizes something. If the assumption is wrong, this changes physics. If it's right, it needs to be proven properly anyway. Either way, it matters. So her decision is simple. Run the experiment. Because in her world, there's only one way to decide what's true. Not debate. Not belief. Measurement. Seeing is believing. July, 1956. Chien-Shiung Wu takes on a problem. Not a routine one. The kind of question that, if answered the wrong way, doesn't just tweak physics. It rewrites it. She doesn't start by arguing. She starts by designing. The goal is clear. Test parity conservation. Not talk about it. Test it. First step, find the right physical process. She chooses cobalt-60. Specifically, it's beta decay. Why? Because this process is governed by the weak interaction. Exactly where the theory is under suspicion. So the target is perfect. Now comes the real challenge. Not running the experiment. Making it clean enough. She's not just measuring decay. She's measuring direction. Which way do the electrons go? Left? Right? Random? But there's a problem. If the atoms are randomly oriented, any directional effect disappears. Averages out. Like watching a crowd run in every direction. You learn nothing about preference. So she needs order. Alignment. She needs the atoms to behave like a disciplined formation. Fall, 1956. She collaborates with the National Bureau of Standards in Washington, D.C. The setup begins. Step 1. Cool the system. Not ordinary cooling. Extreme cooling. Temperatures approaching absolute zero. Where thermal motion nearly stops. Atoms barely jitter. Step 2. Apply a strong magnetic field. Force the nuclear spins into alignment. Think of each nucleus as a tiny compass. Now imagine making all those compasses point the same way. Step 3. Stabilize everything. Eliminate disturbances. No vibrations. No noise. She builds a system so quiet, it's almost unnatural. Only then does the real measurement begin. December, 1956. The critical phase. Detectors running. Data coming in. No one knows the outcome. If parity holds, the electrons should come out symmetrically. No bias. A fair universe. But the data starts to lean. Electrons prefer one direction. At first, it's subtle. Then it keeps showing up. Again. And again. Once as happenstance, twice as coincidence, 3 times as a pattern. But she doesn't jump to conclusions. She repeats. Adjusts parameters. Runs it again. Same result. No drift. No reversal. January, 1957. She confirms it. The data is stable. Errors are under control. And the conclusion is unavoidable. The emission is asymmetric. Which means, the mirror version of the process is not the same. Parity is violated. In plain terms, the universe is not symmetrical. January 15, 1957. The results are finalized. Paper prepared. Data shared with theorists, including Tsundao Li and Chen-Ning Yang. At the same time, other experiments using different methods are running in parallel. They arrive at the same conclusion. Independent confirmation. That matters. Because in science, trust but verify isn't optional. January, 1957. The news spreads through the physics community. No internet, no social media. Still fast, because the implication is massive. A decades-old assumption, gone. No gradual adjustment, no soft landing, just invalid. That's rare. Science usually evolves step by step. This time, it jumps. The reaction is almost universal. Shock first, then acceptance. Because the data is clean. No wiggle room. February 1957. The papers are published. Parity violation is no longer a question. It's a fact. So what does that actually mean? It means that under the weak interaction, nature has a preference, a direction. It doesn't stay neutral. It picks a side. That single result forces theory to adapt. Particle physics shifts. Foundations move. Later, parts of what becomes the standard model build on this idea. This isn't a footnote. It's a doorway. A way into deeper rules of the universe. And at the center of it all, not speculation, not philosophy, data, carefully measured, relentlessly verified. She didn't try to prove she was right. She built a system where nature had no choice but to answer. And the answer it gave was simple. The universe is not a mirror. October 31, 1957. Stockholm. The Nobel Prize in Physics is announced. 2 names. Tsundao Li, Chen-Ning Yang. The citation is clear. For proposing that parity is not conserved in weak interactions. No controversy there. The idea was bold. And it changed physics. But almost immediately, people noticed something else. A missing name. Chien-Shiung Wu. The person who ran the experiment. The person who turned maybe into measured. Not on the list. And this doesn't take years to surface. It comes up within weeks. November 1957. Inside the physics community, conversations begin. Not loud protests. More like quiet, uncomfortable questions. Because everyone understands one thing. A theory without experiment is just a suggestion. Wu's experiment wasn't decorative. It was decisive. Her cobalt-60 setup didn't hint at an answer. It delivered one. Clear. Repeatable. No gray area. No, it might be. Just this is what happens. Later, some physicists would describe her contribution as the critical evidence, not support. The core. So the questions start stacking up. First, how do you weigh theory against experiment? Historically, Nobel Prizes often recognize both. This time, only one side makes the stage. Second, context matters. The 1950s weren't exactly welcoming to women in physics. Female professors were rare. Top-tier experimentalists? Even rarer. Wu wasn't just working in the field. She was already an exception within it. Third, how science hands out credit. The people who propose ideas often become the names attached to them. The ones who test those ideas? Sometimes seen as implementing. But this case doesn't fit that pattern. Her work wasn't routine execution. She designed the experiment, controlled the conditions, drove down the errors, verified the outcome. That's not assisting. That's owning a piece of the discovery. December 10, 1957. The Nobel ceremony takes place. Li and Yang walk on stage. They give their speeches. Everything proceeds as expected. No mention of what's missing. No footnotes. No addendum. History, in that moment, gets written. And it's concise. 2 names. No third. History is written by those who are recorded, as the saying goes. In the decades that follow, the discussion doesn't disappear. It lingers. Some accept the decision. Others don't. But the outcome never changes. Wu never receives the Nobel Prize. She does receive major recognition later, including the Wolf Prize in Physics in 1978. A prestigious honor. Highly respected in the scientific community. But it's not the Nobel. And in public memory, that distinction matters. Over the years, physicists looking back often agree on one point. Her experiment was indispensable. Without it, the theory wouldn't have been accepted so quickly. It might have sat, debated, delayed. But history tends to compress things, simplify them, reduce a complex process into a short list of names. In this case, 2 names made it, 1 didn't, and that absence becomes part of the story. Not just about one prize, but about a bigger question. How does science assign credit? Who gets remembered? Who fades into the background? There's a stark contrast here. The ones who asked the question were awarded. The one who answered it was not. It's not the only example like this, but it's one of the most discussed, because the impact was huge, because the evidence was clear, and because the missing name is impossible to ignore. After 1957, physics loses something it once took for granted: perfect symmetry. Not as a metaphor, on paper, in equations, in the way the universe is described. Parity violation is no longer a possibility. It's built into the theory. Weak interactions have to be rewritten from the ground up. 1958. Physicists, including Richard Feynman, begin reshaping the framework. Out of that effort comes what's known as the VA theory, a new way to describe weak interactions. And at its core is something that used to be unthinkable. Direction matters. Nature isn't neutral. It has a preference. Facts don't cease to exist because they are ignored. And now the facts are unavoidable. The 1960s roll in. Particle physics speeds up. New particles show up one after another. The theory starts to organize itself, piece by piece. Eventually, this leads to what we now call the Standard Model. And built into that model? The asymmetry first nailed down in that 1957 experiment. That's the starting point, not the end. At the same time, experimental physics evolves too. The bar gets higher. It's no longer enough to see something happen. You have to measure it precisely, control it, repeat it. Chien-Shiung Wu's approach becomes a template: low temperature control, strong magnetic alignment, careful analysis of systematic error. These aren't optional techniques anymore. They become standard practice. And they spread, not just in particle physics, but into nuclear physics, condensed matter, and beyond. Raise the bar, and the game changes. That's exactly what happens. On the technical side, beta decay research keeps moving forward. In nuclear engineering, decay data feeds directly into reactor calculations. Accuracy here means safer, more efficient systems. In medicine, radioactive isotopes open new doors. Take PET scans, positron emission tomography. They rely on understanding decay processes at a deep level. Better data leads to better imaging, better diagnostics. Meanwhile, detector technology improves. Higher precision, cleaner signals, more stable systems. None of this happens overnight. It's a long build, layer by layer. And her work sits right at one of the early, critical layers. 1965. She publishes a book, Beta Decay. Not a casual read, a reference, a consolidation of decades of experimental work. Graduate students use it. Researchers rely on it. Not because it's easy, because it's right. Beyond the lab, things begin to shift too. In the 1950s, women in physics are rare. By the 1960s, slowly, that starts to change. Not overnight, but movement begins. And she becomes part of that shift, not just because of her results, but because of where she stands. Top-tier university, core research, visible position. That matters. Representation isn't everything, but it's not nothing either. At the same time, more Asian scientists enter the American research system. She's one of the early figures in that wave. Not the only one, but a significant one. January 1975. She's elected president of the American Physical Society. First woman to hold that role, ever. That's not just a personal milestone, it marks a shift in the system itself. Times change, and we change with them. But sometimes, people are the reason times change. 1978. She receives the Wolf Prize in Physics, a major recognition, specifically honoring her contributions to nuclear physics. It comes more than 20 years after her most famous work. Late, but clear. The evaluation is not ambiguous. Her impact is acknowledged. And her influence goes beyond theory, beyond specific experiments. It moves into methodology. How do you design an experiment? How do you control error? How do you decide if a result is trustworthy? Those questions now have a higher standard, in part because of her. Look at her personally, and the pattern holds. Consistent, precise, demanding. Her rule for data is simple. It's either correct, or you do it again. No middle ground. Students remember this well. They hand in reports. She reads them line by line, finds an issue, points to it directly. Not a suggestion, a correction. If there's a 0.1% discrepancy, she asks why, and keeps asking, until there's a real answer. Measure twice, cut once. Except in her world, you measure 10 times. That approach builds reliability. It also builds pressure. Not everyone finds it comfortable, but it works. In public, she's just as direct. Around the mid-1970s, she speaks openly about women in science. No vague language, no soft framing. She uses facts and lets them speak. At home, her life runs on a similar frequency. She and Luke Chia-Lu Yuan continue as partners in both life and physics. Two scientists, one household. Discussions don't stop when the lab closes. They just change location. They have a son. Family and research move in parallel, not separated, integrated. Later in life, she reconnects more with China. From the 1970s onward, she visits, lectures, shares experience, encourages scientific exchange. Her role evolves from doing experiments to passing on how to do them, but the core never changes. Experiment, measurement, verification, and one guiding principle that never leaves. If you want the truth, you don't argue for it, you measure it. By the 1970s, her name isn't a footnote anymore. It's part of the main story. Open a physics textbook, and Chien-Shiung Wu isn't tucked away in a sidebar. She's a turning point, a place where the narrative shifts. 1976. She receives the National Medal of Science, one of the highest scientific honors in the United States, presented at the White House by the president. She's 63. By then, her work has already shaped an entire generation of physicists. Not just what they study, but how they study it. 1978. Another recognition. The Wolf Prize in Physics. The citation is direct. Her work on beta decay. Her experiment on parity violation. 2 phrases. That's enough. By now, they're inseparable from her name. The 1980s arrive. She begins to step back from daily lab work. Less time running experiments. More time speaking, teaching, traveling. 1981. She formally retires from Columbia University. But retire doesn't really fit. She keeps moving. Visits universities. Gives talks. Shares experience. And her style doesn't change. Still direct. Still precise. No decoration. Just conclusions. Say what you mean, and mean what you say. That's her rhythm. Early 1990s. She's still attending conferences. Older now. But sharp. Clear thinking. No drift. February 16, 1997. New York. She passes away at 84. Quietly. No dramatic headline. No global pause. But within the scientific community, the response is immediate. Institutions release statements. Colleagues reflect. And the message is consistent. She changed physics. Not from theory. From experiment. Her work doesn't depend on awards to exist. It's written into the structure of the field. Now here's the contrast that never quite goes away. The 1957 Nobel Prize still doesn't include her name. That hasn't changed. But something else hasn't changed either. The experimental proof of parity violation came from her work. That part is fixed. Textbooks don't rewrite data origins. Papers don't swap out authors. Science keeps its own record. more stable than any prize list. In the long run, the truth will out. Her life leaves two parallel outcomes. One is written in awards, the other is written in physical law. The first can be debated, the second cannot. Students later recall something she often said in the lab: "Let the data speak." No exact date for that line, but it runs through her entire career. From her PhD work in the 1940s, to the 1957 experiment, to her 1965 book, Beta Decay, to her lectures in later years. Same principle. She never focused on promoting herself. She focused on getting the result right. Recognition? Secondary. Verification? Everything. And that leaves behind two legacies. One specific. She proved that parity is not conserved in weak interactions. And one broader. In science, conclusions don't come from reputation. They come from experiment. Not from who gets the prize, but from what survives measurement.
The people who change the world usually just think one step deeper. If this story made you see things differently, hit like, subscribe, and save it. See you in the next story.